MQ resins, shown here on the right-hand side, are essentially small pieces of silica capped with trimethyl groups. So they have both inorganic hydrophilic and small organic hydrophobic properties. They're of high value, partly because they're not quite difficult to make. They never look as beautiful as this scheme would imply. They're relatively low molecular weight, only between 2 and 10,000 grams per mole. And they're used in things like tackifiers to change rheology or to provide reinforcement when transparency is necessary in elastomers. We were interested in making linear analogs of these just to see if it could be done. Normally, when you have trifunctional T or tetrafunctional Q materials, you end up with elastomers. What happens if you make linear analogs? We took tetramethoxysilane plus this silicon hydrogen compound here in a Piers-Rubinsztajn reaction with this boron catalyst. And although we tried really hard, it was not possible to preferentially make any of these 4 molecules here. The one of interest is this one. It's difunctional, and so it can make a linear polymer. What we had to do, therefore, was distill it to get a pure version of that. And once in hand, it was easy to do more Piers-Rubinsztajn reactions, for example, with sulfenylene, to give alternating sulfenylene branched silicon materials. But the one we're really proud of is the one where we take the simple disiloxane and react it, because now you make a pure methyl silicone polymer with, we think, world record amounts of Q tetrafunctional and T trifunctional groups within them without any elastomers. We were hoping for very interesting properties. Actually, their properties are pretty much like methyl silicones would be. But nevertheless, it shows that we can take advantage of these Piers-Rubinsztajn reactions to make interesting, highly branched materials. The paper in which this is described is in the journal Silicone. It's shown down here. It's an open access paper. Thank you very much for your interest.